Okay, so this is the data from our osmolarity lab where we put potato tissue in different concentrations of salt solution, and we want to find out the osmolarity of the potato tissue. So the first thing I need to do is I need to make sure that the headings of my table are correct. They need to show what the variable is, the measurement uncertainty of whatever that variable is, and the units. In this case, osmoles per liter or moles per liter is the concentration, and mass is precise to 1/100th of a gram. That's the first thing that needs to be true for all tables, and that way we can not have to add those units or that information to every single cell in the column. But the next thing we need to do is make sure that our data agree with that information. Here I'm showing only one decimal place. I should be showing two to show that this is in fact precise to the 1/100th of an osmol per liter. So here's how I do that. I'm going to select all the data and right click, and then I'm going to format those cells. The number of decimal places I'm going to set at 2, and that shows up here. Now if your data is, if there's something going on with your calculations, one of the reasons may be, one of the easy things you can check is whether you're using decimals or periods, decimals or commas, because right now it's expecting commas. If I put a decimal place instead of a comma, it doesn't know what to do with this, and it kind of treats it like text, and so it won't be able to do any calculations with numbers. So if you're having any problems with your calculations, check that first to know what your program is expecting. And I need to go ahead and do that for the rest of these. I could have done that all at once. They all need to be showing 2 decimal places. So I'm going to go ahead and do that first and make sure that my measurement uncertainty agrees with my table. Now it doesn't change anything as far as the calculations. The 0 is assumed by the program, but when you're presenting your data tables, this shows that you know how to communicate using measurement uncertainties. Okay, so I have the mass at the beginning and the mass at the end, and what I really want to find out is the change in mass. So I'm going to make a new column here. Change in mass over 30 minutes. Again, plus or minus 0.01 grams. The measurement uncertainty in units are the same because that's what I'm using to calculate it. And here, in case you haven't learned or forgotten how to calculate in spreadsheets, I'm going to put the equal sign, and then I can click on the cell minus this cell. Now I'm always going to do final minus initial, because that way the sign in this number will be correct. If it's gone down in mass, it'll be negative, and if it's gone up in mass, it'll be positive. And instead of having to type that in every single time, I'm just going to grab this bottom right corner and drag that down. And now it has done the same calculation for each of these cells. But again, I need to make sure that the level of precision is correct with 2 decimal places. Okay, but I'm going to go ahead and show this data as percent change in mass because some of these pieces of potato were a little bit larger than other pieces. They're all right around 10 grams. But we can account for this difference by calculating the percent change in mass. This is a little bit more meaningful measurement. And so this is the percent change in mass. And this is plus or minus 0.1%. We lose a little bit of precision when we're calculating percentages because we're moving the decimal place around. For our intents and purposes, we're going to use, so I'm going to stick with commas so that I'm being consistent here. Now, when you go to publish your work for the IB, you'll want to do these all as decimals. I'm not going to take the time right now to change my program around to use decimal places. But let's go ahead and do this calculation. To calculate percent change, it is the final minus the initial divided by the initial. But now I need to go back and double check that it's going to do the right order of those calculations and make sure it does this subtraction first. So I put this subtraction in parentheses. Now it's going to take this value and divide it by that value. So that's one way to do it if I want to do it all by itself. Another way to do it, since I've already done this first calculation, would just be to take this value and then do it for all of them. Now I'm going to format the cells, and I'm going to tell the computer that these are percentage and that I only want one decimal place. And it automatically does the times 100. So you can see these are all out of order. This was just the order that the students gave me their data. So I'm going to go ahead and sort this data so that it's a little easier to see what's going on here. Data sort. I'm going to sort it based on column A, concentration, and that cleans things up so I can see what my concentrations are and what these values are. Okay, so that takes care of the raw data table. This is one data table that you will include in your analysis portion. When you go to put this in your word processing document into your report, you'll want to clean this up so that maybe the titles are bold and it's cleaned up and easy to read. The spaces of the columns fit on your document. Do some formatting on it so it's just easy on the eyes. Right now I'm just worried about the numbers because I'm just doing my calculations, but keep that in mind. That's an important aspect as far as presentation, making your data tables nice to read. So the next thing I need to do is make what's called a summary data table, which is going to include the averages and standard deviations for each of the concentrations. So I'm just going to go ahead and copy this. Then I've got the 5 different concentrations, and I'm going to just go ahead and enter these by hand. I guess it's 6 different concentrations. Fine. Again, set the correct level of precision. Cells. 2 decimal places. And then this is going to be the average percent change in mass. Again, the same units, plus or minus 0.1%. It's supposed to be in parentheses. Okay, now I need to go ahead and calculate the average. So this is equal to the average. And if you're working on a German computer, you're going to type in the same thing, equals, aber dann Mittelwert, and it should show you this information about what you're expected to put in here. And I'm just going to add the values for 0, these first 3 values. Okay, and do that for each of these. Looks like there's more measurements for this one. Make sure I include this last one as well. And 4. Okay, those are the averages. Now I need to take the standard deviation for each of these. which will show me the variance that's involved with this average. It will tell me if the measurements used to calculate this average are close together or if they're far apart. And that is STDEV in English. If you're working in German, it is STABW.N, Standardabweichung Punkt normal. So I'm working in German, so I've got STDEV, working in English, not German. And then it's asking for the same information as for the average. So it needs to know which numbers were part of that average. And just go ahead and do that for each of these. Okay, need to format these cells. They have the same units and precision as the average they're associated with. So 1 decimal point, percentage. And then I can go ahead and rename. I name this is the standard deviation. And again, the measurement uncertainty and the precision are the same as the average that they calculated from. So this would be my summary data table, showing just getting right to the main information here. I've got an average for each value that I tested and the standard deviation. And this definitely needs to go in the analysis portion. But we're also going to make a graph using this data. So I'm going to go ahead and do that next. And again, make sure your tables are readable when you put them in your word processor. I'm not going to take the time to do that right now because I'd have to do it again when I put it in my text. So right now I just want these values to make what's called a scatter plot. So I'm going to insert the chart. And, oops, be sure not to use a line chart, even though these look very similar. They function differently. So this is what's called a XY scatter. The data ranges, it's usually pretty good at figuring out on its own. That looks about right. The data series are also correct. The chart elements I definitely want to include. Give your chart a meaningful title that is clear to your reader exactly what this chart is showing. Meaningful titles are usually pretty long and descriptive. The x-axis is the concentration. And again, always include the measurement uncertainty. And the units. And the y-axis is the change in mass. Average percent change in mass plus or minus 0.1%. And go ahead and finish that. Okay, so I don't need a legend because I only have one type of tissue here. If I had different types of tissue, like the example we looked at in our textbook, I would need a legend to know which color meant which. But since I don't have that, I can go and get rid of that. I'm going to leave the title writing up to you. I want you guys to think about that, how you would title this. But now I need to include this standard deviation data. And the best way to represent standard deviation data is with error bars. So I'm going to insert Y error bars because these are associated with the Y axis. These aren't X error bars that would be some error in the concentration. But we set the concentration at what it was, and we're very precise about that. So I'm going to insert y error bars. And there's a couple different options for how to do this. This option, although this looks right, the standard deviation, this calculates the same standard deviation for all of the data points, and that's not what we want. We want to give it a cell range, because I'm going to show the computer which cells I want to include. I have to move my chart out of the way, because it's right here. Cancel. I'm going to get this out of the way first. That. Okay. So I'm going to click on the data points, right-click, insert y error bars, and I'm going to give it a cell range. This is for the positive, and the same thing for the negative. These are my standard deviation values that I've calculated. Now you can see I've got these error bars that show, okay, this is the average, but there's a lot of variation in this data point, so it could have been somewhere up here, or it could have been somewhere down here. I'm not really sure exactly where it is in here, because there's a lot of variation. So we see in the first and the last, there's a lot of variation, but in some of them we have really reliable measurements that they're very repeatable. Here and here, for example, we have relatively small standard deviations. So that standard deviation shows, again, the variation in the data, and that's important to include. Then, as you can see here, my error bar is going off the bottom of the chart, so I need to change my chart axis. I need to format the axis so that I can see all of this data, because otherwise I don't know how far this standard deviation bar goes down when I look at it. I'm going to format axis, and the minimum is currently set to automatically be minus 15%. Let's see if it shows up at minus 20%. We need to go to 25. Let's see what that looks like. Okay, so I just set that to minus 25 in this case in order to capture this. So make sure that all your data and all your error bars are all on the chart. And I don't really care to show this value because there's no data all the way over here. So I'm going to format the x-axis as well and set the maximum to 0.5. That way I can just see all my data in here. Okay. So I have my averages and standard deviations plotted. I've scaled the axes. I have the axes labeled. You've already written a meaningful title across the top. The last things we need to do is we need to add a trend line. So I'm going to insert insert trend line. So you have to select the data points first. I got a little bit lost there. Select the data points first and insert a trend line. And we've got a couple options as far as our trend lines as well. First of all, we want it to be linear in this case. Sometimes you may encounter logarithmic or exponential trends. This one we happen to know is a linear trend. I don't need to name it, but I do need to show the equation and show the coefficient of determination, R squared value. And then I can go ahead and move this to somewhere that I can read it. So this is the equation that we're going to use to solve for the y equals 0 case. So we're going to set f of x to 0 and solve for x, and that will tell us where this line crosses the x-axis, and that is the estimated osmolarity of the tissue. That's where, at this concentration of salt solution, we wouldn't expect the tissue to gain or lose any mass due to osmosis. That takes care of the calculations and everything, but as you might have noticed as we were going along here, some of these data points look a little bit strange. For example, down here at 0.5, I've got 4 data points. These last 4 data points were in a 0.5 molar salt solution. And one of the data points looks really, really different. And this is what we call an outlier. And what do you do with outliers? Well, outliers are oftentimes the most interesting data points sometimes something different happened here for some reason, and this measurement is showing you that this was some different effect. Now, it could have been a mistake. It could have been that you've forgotten to tear the scale, or you included the mass of the beaker or the paper towel or something else like that. Maybe a piece of potato tissue went missing or something like that. This looks like this mass change could have been due to a missing piece of potato tissue, for example. It's hard to say, since I didn't take these measurements, what happened here. At this point, it would be really important to go back to your notes that you took for yourself during the lab, during your experiment, to find out what might have happened here. Maybe it was just a copying error. Maybe you misread your numbers, your handwriting or something, and you can solve it that way. If everything seems to have gone correctly in your experiment, or you can't find an easy explanation for it like that, then you generally need to go back and repeat this measurement to see which of these data points are the correct ones. If this is the correct data point and these three were all mistakes due to some measurement error, we need to know that. And so the second thing you can do is go and repeat that part of the experiment to verify your data. And if you repeat it again and you get 4 or 5 measurements all right around the -7 or -8%, then you can safely assume that you did something wrong with this, and you can leave this out of your calculations. That being said, whenever you decide to leave a data point out of your calculations, you need to declare that A, you've done that you've decided to exclude this from your calculations, and B, you need to justify why you've done that. Now, if you have some plausible explanation why you think this was a mistake, you can include that in your analysis. And this would also go in the analysis portion. So it may be worthwhile, for example, to put this under an asterisk, and therefore it won't be included in this graph, but this data point would be included in the data table that you do publish, so that you're showing your readers, okay, I had this data point, it has an asterisk next to it, and right below the table, the asterisk is explained why this data point wasn't included, for example. So if you did that, it would change. I'm just going to put in here asterisk, if I can find it. I'm just going to put in -27, what was it, 26.8. I'm going to use a point, and that way it doesn't recognize it as a number. Oh, it's not working now. I can't calculate with that. Let's see here. Oh, no, that did work. It's still there. Okay, so you can see then if I eliminated this from the calculations, it's no longer calculating with this number, that these three are very similar, and the standard deviation here has dropped to 0.5%, and it's hard to see, but the error bar is smaller than the data point there. And that's, of course, going to change the value for this line, and will change your calculations dramatically. So if that happens to be the case, that you have some strange data points that you can't explain in your data, you may need to take them out of your calculations. If you do that, explain why you did that. Now, the R-squared value here tells us how well basically this line fits the data. And it's a number between 0 and 1. A 1 would mean that the line hits every single data point. It's a perfectly straight linear regression. And lower values like this one, 0.64, 65, mean that there's a lot of variability in the data. So we'd expect this all to be a perfect line. This first data point seems like it's not fitting that trend. Maybe there's some reason. We can go back and repeat this experiment, find out why this didn't behave the way we expected it to, or maybe this is really what the data is showing us, in which case we need to come up with an explanation for why this doesn't match the trend. And I suspect if, for example, this data point were somewhere up here, we would have a much higher R-squared value, probably in the 0.8, 0.9 range. And reporting about and analyzing this R-squared, you need to include this in your analysis and talk about how reliable your data are, how strong the trend is. If you have an R-squared above 0.8, for example, you have relatively strong trend and a strong correlation between your independent variable and your dependent variable, for example. The last thing you'll need to do in your analysis portion is to show the math how you've solved this equation for y equals 0 and explain that calculation, what you've done and why you've done that, and to give your final conclusion. So in your analysis portion, you'll need to include the raw data, the summary data, the average and standard deviation, this graph. Again, each of these tables needs their own descriptive title. Each column needs to be labeled as we've gone along and done with the proper variable, measurement precision, and units. And then you're not done. Then you need to go and in text form explain and describe the data in detail, especially anything that doesn't quite fit the trend. Talk about what the trend is, how strong that trend is, and all of the data, just describing in words what you've put in tables and graphs. You don't ever want to include a graph or a table in scientific writing without talking about it in the text and referring back to it in the text. Okay, so that should help you along here.